Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today, we'll talk about double integrals. First, I want to recall to your memory the definition of the Riemann integral. Way back in Cal1, we had some function, y equals f of x, between x equals a and x equals b. The goal was to calculate the area of the undergraph. The way we did that is we partitioned the domain at x1, a was equal to x0, x2, and so on. They didn't all have to be equal width. We defined the integral from a to b of f of x dx to be the limit. Now, the norm of the partition, also called the mesh, was equal to the maximum of the delta x k's. The maximum of the subinterval widths. They didn't all have to be the same width. They could be different widths. So we would take the limit as the maximum subinterval width goes to 0, the sum as k goes from 1 to n. We chose sampling points within each interval, f of ck times delta x sub k. This allows for sampling points to be taken anywhere within each of the little partition subintervals, and delta xk allows for different width subintervals. This was the definition of the Riemann integral. You'll also recall the fundamental theorem of calculus, which said that you can calculate a Riemann integral if you can find an antiderivative by evaluating the antiderivative at the endpoints and subtracting. This was nearly miraculous. There was no reason to believe that anti-differentiation, the opposite of differentiation, had anything to do with area finding. But in fact, we find that slope finding and area finding are actually inverse processes. For double integrals, we're going to suppose that we have a function of, say, two independent variables. F is going to map some domain contained in R2 into the set of real numbers. We already know that equations of this type represent surfaces in R3. So let's suppose this is our domain here. What we're going to do is we're going to partition the domain, but we're going to partition it in two directions, making little rectangles. We'll have these little rectangles, r sub k, in the domain. Now, how do we determine the partition size? We have a partition, which is going to be this slicing up of the domain. The norm of the partition for each of those little r sub k's, we have a diagonal. It's going to be the maximum over all the different k's of these diagonals on that r sub k. That's going to determine the size of the partition. By sending the maximum diagonal length to 0 will cause not only the change in the x direction to go to 0, but also the change in the y direction to go to 0 at the same time. So we'll define the integral over this domain of some function f with respect to an element of area, the limit as the norm of the nth partition goes to 0, the sum as k goes from 1 to n, f of, just as before, we will select sampling points, but these will be points c vector k And each of these little r sub k's will have an area. We'll call that delta A sub k. This gives us a notion of what does this represent then? Notice if we take the function value, that's giving me a certain height. If we multiply that by this area of the rectangle down here in the base, area times how far it swept, by the theorem of Pappus, gives us a little bit of volume, a little piece of volume. If you add up those little pieces of volume under the surface, what you end up with is the volume of the region underneath this surface patch. The Riemann integral from Calculus 1 gives you the area of the undergraph. These sorts of Riemann integrals in Calculus 2 for double integrals represent volumes of the undergraph. There's another way of looking at these, though, using something called Cavalieri's principle. Cavalieri was looking at wine barrels. Now, these wine barrels, he wanted to calculate the volume of the wine barrels. He figured he could do it about like this. You take a thin slice of the wine barrel. Instead of taking into account these bent edges, suppose that they're just like flat stacks. What you can do is you can find the area of one of the faces here, a little area at each, say, x. We'll have an axis here, and we'll measure the area at some height x off of the bottom. If you multiply that by some thin little delta x, you get a little element of volume. The total volume can be approximated as the sum as k goes from 1 to n. If we slice these at, say, x sub k, we'll do the area at x sub k times a delta x. It just adds these up by slices like this. This is actually pretty close to a Riemann integral. All you need to do is take a limit. Let's apply this Cavalieri's principle to double integrals. And in particular, let's suppose that we're looking at a situation where the domain looks as follows. If this is the x-axis, y-axis, and z-axis, we're going to assume the domain goes between a and b on the x and between a lower curve and an upper curve. Let's call this upper curve y equals let's call this upper curve y equals g2 of x and the lower curve y equals g1 of x. We'll have our surface up here. And we are going to get the volume, but we're going to do it as follows. We're going to have x be fixed. And we're going to take a slice right on through the region like this. In fact, we're going to take a little thin slice of width dx. If you look at the piece of surface just above, what you can do is you can calculate the area at x of this piece and then multiply by dx to get an estimate for the volume of the thin slice. So your little element of volume will be the area times dx. Now, how do you calculate that area? Well, the area is going to be an integral from the lower curve, g1 of x, to the upper curve, g2 of x, of your function f of x comma y, where you're holding x constant and integrating with respect to y as y ranges between these values. You're going to multiply that by dx, and that gives you an estimate for the volume of the thin slice. The total volume can be calculated by adding these little thin sliced volumes up as x ranges from A to B. This gives you something called an iterated integral. Integrals, because you do the inner integral first on this function holding x constant, and then you do the integral with respect to x second, yielding a constant value when all is said and done. This leaves open the question, can you always calculate double integrals using iterated integrals? Now, iterated integrals may be evaluated using the fundamental theorem of calculus, which means this reverts back to methods from Cal1. It's unclear if you're integrating over some domain FDA, a double integral, which may also be written with this form. I often determine whether or not it's a double integral based upon the kind of element that you have here. If it's an element of area, that means you're going to be doing two integrals. Even though you may write it with only one, it's really going to involve two when all is said and done. I want you to be able to understand what I'm talking about, because this is common notation. Use only one integral even though you're thinking of a double integral. I want you to be aware of that. We are going to have a sequence of theorems. One of them is called Fubini's theorem. Fubini's theorem tells you that all double integrals can be evaluated using iterated integrals. That's good news because that means you can calculate your double integrals using the fundamental theorems of calculus. If D is described by A is less than or equal to X is less than or equal to B, and G1 of X is less than or equal to Y is less than or equal to G2 of X, so your domain in the XY plane is described by a lower curve and upper curve, an A and a B. You have a G1 of X and a Y equals G2 of X. Then the integral on that domain of FDA is equal to the integral from A to B, the integral from G1 of X to G2 of X, f of x comma y, dy dx. The order in which you write dy and dx makes a difference. The dy here is associated with the first innermost integral. That's the integral you must do first. And then the dx is associated with the outer integral, with the constant x limits of integration. This is the region D. The surface lies above that in the z-axis direction. In this particular order, we say that we are using vertical cross sections. We have a little dx here. If we're viewing this from above, we go from lower curve to upper curve. From lower curve to upper curve. Looking from this direction, you see this one first, and then this one last. First and last. And you go from left to right on the x-axis. There's another version of Fubini's theorem for what are called horizontal cross-sections. If D is described by c is less than or equal to y is less than or equal to d, and then g1 of y is less than or equal to x is less than or equal to g2 of y, then the integral on d of f dA is the integral from c to d, the integral from g1 of y, g2 of y, f of x comma y, dx, dy. Dx dy if it's horizontal cross sections. In this case, you have c and d as your outermost limits of integration, and then a curve x equals g1 of y, x equals g2 of y, and this is the domain D. If the domain is described in this way, you have what are called horizontal cross sections. On the horizontal cross sections, you look from left to right. You end up seeing this curve first and this curve last in the region, and then you progress from lower y values to larger y values. I want to look at an example. I want to suppose my function is 1 plus 3x minus 4y squared dA, where the region D can be described by, let's use x goes from 0 to 1 and y goes from y equals 0. That's the expression for that lower curve. The upper curve will make y equals x. We will use vertical cross sections first and then use horizontal cross sections next. So by Fubini's theorem, this should be the integral from 0 to 1, the integral from y equals 0 to y equals x, 1 plus 3x minus 4y squared dy dx. Integrating with respect to y first, we get y minus, or rather plus, 3xy minus 4/3 y cubed, evaluated from 0 to x. This gives us the integral from 0 to 1. We plug in x for y now. That's going to be x plus 3x squared minus 4/3 x cubed, and then minus 0. This gives us x squared over 2 plus x cubed minus, we'll have x to the 4th over 4. The 4 will cancel. I'll have minus 1/3 x to the 4th. This is evaluated from 0 to 1. Plugging in the 1, we get 1/2 plus 1 minus 1/3 and then minus 0. 1/2 plus 1 is 3/2 minus 1/3. That's going to be 9 minus 2 is 7/6. This gives us the volume underneath this surface above this triangle. Now, we calculated this particular volume using vertical cross sections. We're going to go back and calculate that using horizontal cross sections instead. For horizontal cross sections, we take the slices in this direction and view it from this side. This will be the lower curve. This will be the upper curve. We'll go from here to here, 0 to 1. The lower curve is x equals y. The upper curve is x equals 1. Now I want you to pay special attention to how we set up the limits of integration here. The limits of integration are not going to be the same as last time. We're going to get the integral as y goes from 0 to 1, and as x goes from y to 1. This time it's going to be dx dy. We integrate with respect to y last. Integrating with respect to x, we have x plus 3/2 x squared minus 4y squared x evaluated from 1 to y dy. Plugging in 1 for x, we'll have the integral from 0 to 1 of 1 plus 3/2 minus 4y squared minus what you get when you plug in y for x. That's y plus 3/2 y squared minus 4y cubed. Let's simplify before we evaluate. We have the integral from 0 to 1. The only constant is 1 plus 3/2. That's going to be 5/2. We have a minus y. We have a minus 4y squared and a minus 3/2 y squared. This is 8/2, another 3/2. That's minus 11/2 y squared. Minus minus makes plus 4y cubed. Note how different this computation looks at this point than integrating in the other direction using vertical cross sections. Do you really get the same value? 7/6? Fubini's theorem says you do. Let's see. We'll have 5/2 y minus y squared over 2 minus 11/6 y cubed plus y to the 4th evaluated from 0 to 1. We have then 5/2 minus 1/2 minus 11/6 plus 1. 5/2 minus 1/2 is 4/2, or 2. Plus 1 is 3. How many sixths is 3? It's 18/6. Minus 11/6 gives us 7/6, just as before. I want to review what we just did here because it's highly likely that many of you kind of missed the point. So let's review. The region that we're integrating over in the domain, the xy plane, was a triangle. We first used vertical cross sections. In vertical cross sections, you look from below. You go from lower curve to upper curve and from left to right. From left to right would be 0 to 1, and from lower curve is y equals 0 to y equals x. We have the integrand dy dx. Since these are y limits, we'll integrate with respect to y. These are x limits. For those, we integrate with respect to x. Now, do you get the same thing if you integrate with horizontal cross sections? For horizontal cross sections and the same region, you integrate from y equals 0 to y equals 1, y equals 0 to y equals 1, where this intersects, and from lower curve to upper curve from the sideways perspective. The lower curve is x equals y, and the upper curve is x equals 1. dx dy. X limits go with the infinitesimal dx, y limits with the infinitesimal dy. These two integrals look so different, and they have very different elements in the steps leading up to the final answer. Fubini's theorem guarantees you will get the same answer. And in fact, we saw that both of these integrals give us 7/6 as the answer. So we can calculate this double integral. It is a double integral because of the element of area. This is defined as a limit of Riemann sums, but Fubini's theorem says you don't have to do a limit of Riemann sums. Instead, you can use iterated integrals and reduce the whole thing to the fundamental theorem of calculus. That's the beauty of Fubini's theorem. No limits of Riemann sums, just iterated integrals. So Fubini's theorem is similar in that sense to the fundamental theorem of calculus from Calculus 1. The fundamental theorem said you don't have to do limits of Riemann sums, just find an antiderivative, evaluate the endpoints, and subtract. Fubini's theorem says you don't have to do limits of Riemann sums, just do two single integrals and apply the fundamental theorem of calculus twice. By the way, if you're integrating over some region just the area element where the function f is identically equal to 1, then what you end up with is adding up elements of area over the region, you get the area of the region. Let me give you an example real quick. Let's suppose the region is described by the region bounded between the x-axis, which is y equals 0, and y equals sine of x, as x goes from 0 to pi. The area is equal to a double integral. We'll use vertical cross sections, dy dx. That will take us as x goes from 0 to pi, and as y goes from the lower curve is y equals 0, to the upper curve, which is y equals sine of x. Integrating with respect to y, we get the integral from 0 to pi of y evaluated from 0 to sine of x dx, which gives us the integral from 0 to pi of just sine of x minus 0 dx. We already know that that's one bump, and one bump gives you 2. There is a basic theorem describing the properties of the double integral that only relies on the definition of the double integral in terms of limits of Riemann sums. First, the integral over some region of a constant times f is a constant times the integral of f over the region. So in other words, constant factors can be factored out of double integrals. The integral on r of f plus g dA is the integral on r of f dA plus the integral on r of g dA. Duh. You can see how both of these follow from the limit of Riemann sums version of the definition. On your limit, both constants pull out of limits and out of sums, so you can see them coming out. Sums can be broken up across plus or minus, and then you can take the limit across each of the resulting terms. So these follow very quickly from the definition. Third, suppose f of x is bigger than or equal to 0 for all x that lie within the region R. What does that tell you about the double integral of f on that region? Well, whatever it is, it can't be negative. As an immediate corollary to part 4, if f of x is always bigger than or equal to g of x, for all x that lie within the region R, then the integral on r of f dA will be bigger than or equal to the integral on r of g dA. There is another part. Suppose the region R looks something like this, but the region can be decomposed into region 1 and region 2. So in part 5, let's suppose that R is R1 union R2, but let's also suppose that there's no overlap. R1 intersect R2 is empty. Then when we integrate on R f dA, you can break this up as the integral on region 1 plus the integral on region 2. This is similar to a principle for single integrals that you learned in Cal1. The integral from a to c of f plus the integral from c to b of f equals the integral from a to b of f. So back in Cal1, if you had a function from a to b, you could break it up and go from a to c and then c to b and get the whole thing. Do you remember how to calculate the average height of a function from Cal1? The average on some interval a to b of f was the length of the interval times the integral from a to b of f dx. Here, the average on some region R of f will be 1 over the area of the region times the integral on R of f dA, calculated in pretty much an analogous fashion. There is a corollary to Fubini's theorem that is sometimes referred to as Fubini's theorem, and it goes like this. Let's suppose your region R goes from A to B, but it also goes from C to D, just this rectangle. According to Fubini's theorem, if you use vertical cross sections, you'll go from A to B and then from y equals C to y equals D. Fubini's theorem tells you have to get the same thing if you use horizontal cross sections. There, y goes from C to D, and then you go from x equals A to x equals B. In other words, if all of the limits of integration are constants, you may simply reverse the order of those limits of integration, reverse the order of the differentials at the end. Let's do a quick example. Let's suppose we're integrating from 0 to 1 and from 0 to 2. Let's say x plus 3y dy dx. According to this corollary to Fubini's theorem, you should get the same thing if you integrate from 0 to 2, 0 to 1, x plus 3y dx dy. Let's see if that's true. First, we integrate with respect to y. This gives us xy plus 3y squared over 2 evaluated from 0 to 2 dx. That will be the integral from 0 to 1, plugging in 2 for y. We get 2x plus 2 squared is 4, divided by 2 is 2, times 3 is 6. Integrating with respect to x, we get x squared plus 6x, evaluated from 0 to 1. That's going to be 1 plus 6, or 7. Let's evaluate it the other way now. This variant of Fubini's theorem that says if you have constant limits of integration, you may unthinkingly simply reverse the integrals and the differentials yields this. We integrate with respect to x first. That'll be the integral from 0 to 2 of x squared over 2 plus 3xy evaluated from 0 to 1 dy. That's the integral from 0 to 2, plugging in 1 for x, we get 1/2 plus 3y all times dy. Now, integrating with respect to y, we get y divided by 2 plus 3y squared divided by 2 evaluated from 0 to 2. Plugging in 2, we get 1 plus 2 squared is 4, divided by 2 is 2, times 3 is 6, and again, we get 7. This setting up the limits of integration using vertical and horizontal cross-sections is an important skill that you must possess. In the next example, let's calculate the integral over the region R of x plus y squared dA, where the region R is y equals the square root of x. Let's say we go to 4, that goes to a height of 2, this region right here. If we use vertical cross sections, x will go from 0 to 4, y will go from lower curve to upper curve. The lower curve is y equals 0. The upper curve is y equals the square root of x. Since we're using vertical cross sections, it will be dy and then dx. These were y limits. These were x limits. This gives us the integral from 0 to 4 of xy plus y cubed over 3, evaluated from 0 to the square root of x dx. This gives us the integral from 0 to 4. When we plug the square root of x in, x times the square root of x is x to the 3 halves. But when we cube x to the 1 half, that's also x to the 3 halves. One of them plus a third of them makes 4/3 of them. Now, the fundamental theorem of calculus, you add 1 to the exponent, and divide by the new exponent. That'll give us a factor of 2/5, evaluated from 0 to 4. When you plug a number like 4 into an expression having a rational exponent, make sure you do the bottom first, the square roots. The square root of 4 is 2. 2 to the power 5? You should know 2 to the power 5. 2 to the power 5 is 32. Let's review these. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. And 2 to the 5th is 32. We're going to have 32 times 8/15. This is 240 plus another 16 is 256 divided by 50. Let's try this using horizontal cross sections instead. Our region had y equals the square root of x, which is x equals y squared. Y is going to go to 2. With horizontal cross sections over this region, we'll go from lower curve to upper curve. The upper curve is x equals 4. The limits of integration will be y goes from 0 to 2. Our little cross sections will be taken from 0 to 2. Then we go from lower curve, x equals y squared, to upper curve, x equals 4. Of the integrand x plus y squared, dx dy this time. These were y limits. These were x limits. Integrating with respect to x, we have x squared over 2 plus xy squared evaluated from y squared to 4. Plugging in 4, you get 16 over 2, which is 8, plus 4y squared, minus what you get when you plug y squared in. That's going to be y to the 4th over 2 plus another y to the 4th. A half y to the 4th plus y to the 4th is 3 halves, y to the 4th. Integrating now with respect to y, we'll have 8y plus 4/3 y cubed minus, here we had 3 halves, it's going to be y to the 5th over 5. That's going to be 3/10 y to the 5th evaluated from 0 to 2. This gives us 16 plus 8 times 4 is 32/3 minus 2 to the 5th is 32, but we can cancel. We'll get 16/5 times 3 is 48. One easy way to simplify expressions of this form is to factor out as much as you can first. Each of these 3 terms has 16 as a common factor. That leaves us with 16 times 1 plus 2/3. 3/3 plus 2/3 is 5/3 minus 3/5. How do you subtract fractions? If you have a over b minus c over d, you need to have a common denominator. So you'll multiply the first fraction by d over d and the second fraction by b over b. So that gives you ad minus bc over bd. So anytime I'm subtracting, so if I'm subtracting a over b minus c over d, you cross these and then multiply straight across. We have then 16 times 25 minus 9 over 15. 25 minus 9 is 16. 16 times 16 is 256. The same answer as with vertical cross sections. It had better be the same. Fubini's theorem guarantees it. Remember that when calculating the area of a plane region using a double integral, you simply integrate over that region the area element. Let's suppose that we're looking for the area of the region between y equals 2x squared and y equals 2x plus 24. So what is this region? Y equals 2x squared is a parabola going through the origin. Y equals 2x plus 24 is a line going through 24. If we're going to find the area of the region between these two, we should probably use vertical cross sections rather than horizontal. If we use horizontal cross sections, we'll have a bottom curve here and a top curve here, but if we integrate over this other region, it's a different bottom curve. That means you would have to break it into 2 double integrals. Using vertical cross sections, you only use 1 double integral, but you do figure out where these points of intersection are. To that end, we'll set the 2 curves equal to each other. We can divide a 2 off and then move everybody to one side, and then factor. Make sure that you move everybody to one side and 0 on the other. That's how you solve equations like this. You factor. The factors of 12 are going to be 3 and 4. They'll have opposite signs and the larger one will be negative. So we have x equals minus 3 and x equals 4. The area of the region is then, using vertical cross sections, the integral from minus 3 to 4, and you go from bottom curve to top curve. The bottom curve is the parabola. The top curve is the line. And you're just integrating the element of area, which is dy dx. Integrating with respect to y, you get y evaluated from 2x squared to 2x plus 24 dx. This reduces to exactly what you would have done in Calculus 2. You take the top curve and you subtract the bottom curve. Isn't that exactly how you would have done this in Cal 2? Integrating now with respect to x, we have x squared plus 24x minus 2/3 x cubed evaluated from -3 to 4. By the fundamental theorem of calculus, you plug the 4 in first. That's going to be 16 plus, when you take 4 times 24, make sure you've multiplied backwards. It's easier. 4 times 20 is 80 plus another 16. That's 96. Then you get 4 cubed. 4 squared is 16 times another 4 is 64 times 2 is 128. Then you subtract what you get when you plug in the -3. -3 squared is +9. We're taking -3 times 24. 3 times 24 is 60 plus another 12 is 72. That's minus 72. Negative cubed is still negative, times another negative is positive. 3 cubed divided by 3 is 3 squared, or 9 times 2 is 18. Now, 16 plus 96 is what, 112? 9 and 18, we have minus 27, minus minus is plus 72, and then minus 128 thirds. 112 plus 72 is 184. Minus 27. Minus 27 is 160, and then subtract another 7 is 157. We need to convert to thirds, so I'm going to multiply by 3 over 3. That's 300, 450, and 21 is 71. Minus 128 over 3. That's 350, and then minus another 8 gives you 343 over 3. When defining double integrals, we partitioned the domain in the plane into little rectangles and took the limit as the largest diagonal went to 0. No one really wants to calculate integrals that way, so we quickly used Cavalieri's principle to derive Fubini's theorem. Fubini's theorem allows you to use iterated integrals, each of which applies the fundamental theorem of calculus in order to evaluate. However, Fubini's theorem allows you to use either vertical cross-sections or horizontal cross-sections. You need to know how to set those integrals up both ways. Fubini's theorem guarantees that whether you use vertical cross-sections or horizontal cross-sections, you will get the same result. Sometimes, integrating with one type of cross-section is impossible, while the other cross-section is doable. You'll find out. If all of the limits of integration are constant, then you may simply reverse the order of integration without much consequence. You have to change the differentials too. These double integrals give us essentially volumes underneath surfaces above some region in the domain. If the integrand is 1, however, you simply end up with the area of the domain region.